A desert city can drink from a mountain miles away with no pump, no engine, and almost no evaporation. That sounds impossible because deserts do not just lack water, they destroy water in plain sight. Open canals lose it to heat, wells run dry if too many people pull from them, and hauling water by animal limits how large a city can grow. Yet for more than 2,000 years, communities across Iran, Central Asia, North Africa, Arabia, and beyond used an underground machine made mostly of gravity, patience, and human labor. It was called a Qanat, a gently sloping tunnel that collects groundwater uphill and carries it underground to farms and cities downhill. Think of it as a hidden river built by hand. The surprising part is not just that Qanats worked. It is that many worked for centuries, long before electric pumps made deep groundwater easy to steal faster than nature could replace it. To understand why, start at the edge of a desert mountain. Rain and snow fall in the highlands. Some water rushes away in floods, but some sinks into gravel and sand at the foot of the mountains, forming underground water stored in an aquifer, which is simply a layer of earth or rock that holds and slowly releases water. If you dig a vertical well there, you can reach it, but every bucket must be lifted. A Qanat solved a different problem. Instead of lifting the water up, it gave the water a path down. Builders started near the settlement, where water was needed, and dug a tunnel slightly uphill, toward the water-bearing ground. The slope had to be gentle enough that the tunnel would not become a destructive torrent, but steep enough that water kept moving. When the tunnel reached wet ground, water seeped into it and flowed by gravity all the way back to the surface outlet. The city received a steady stream without fuel. From above, a Qanat barely looks like an engineering system. It often appears as a dotted line of holes crossing the desert. Those holes are vertical shafts, spaced along the tunnel. They were not wells for drawing water. They were construction access points, air shafts, and maintenance entrances. Workers lowered tools, pulled out spoil, and later climbed down to clear collapses or sediment. The real infrastructure was the dark horizontal tunnel connecting them below. This design solved one of the desert's harshest contradictions. Water had to travel, but the sun could not be allowed to touch it. In an open canal, hot dry air can take a huge share through evaporation. Underground, the water stays cooler and shaded. It can cross miles of hostile ground while losing far less. The Qanat was also a kind of safety valve. Because it tapped groundwater by gravity rather than suction, it usually could not pull water from below the level of its tunnel. That did not make it automatically sustainable, but it limited how aggressively people could drain an aquifer compared with modern powered pumps. Its flow often rose and fell with seasons and long-term recharge. People had to live with the water the landscape delivered. That limitation helped shape entire societies. In places such as Iran, some Qanat supplied drinking water, orchards, gardens, bathhouses, mills, and fields. Water rights became precise and valuable. In many communities, time itself became a measuring tool. One farmer might receive flow for a fixed number of hours before gates or channels sent it to the next. The technology was physical, but it also depended on rules, trust, and maintenance. A tunnel could not survive if everyone only took water and no one cleared the underground passage. The engineering was ingenious, but the construction was dangerous and brutally difficult. A mother well, the first deep shaft near the water source, could descend far below the surface. From there, tunnel diggers worked by lamplight, with simple tools, following tiny changes in slope through unstable earth. Too flat, and the water would stagnate. Too steep, and erosion could wreck the channel. Hit the wrong layer and the tunnel might collapse or miss the aquifer. Modern surveys can measure old Qanats, but many were originally built by specialists using experience, observation, and astonishing practical geometry. The system spread because it solved a real problem in a repeatable way. Qanat-like systems appear under different names: Kharez in parts of Central and South Asia, Fagara in North Africa, and Aflaj in Oman. Historians debate exact origins and routes of diffusion in some regions, but the core principle is clear. Underground gravity drainage let people move water from wetter highlands or alluvial fans into dry settlements. Some examples are now protected as heritage sites, including Persian Qanats recognized by UNESCO. The numbers can be remarkable, but the human consequence matters more. Where the surface looked nearly empty, the underground could be organized like a water network. There is a reversal here. Today, when people imagine advanced water technology, they picture steel pipes, diesel pumps, electric motors, and concrete treatment plants. A Qanat looks primitive by comparison. But in its environment, its simplicity was the point. It required no imported fuel, it produced little surface evaporation, it could be repaired with local knowledge, it matched water delivery to gravity instead of forcing gravity to surrender. For a desert city, that was not backward, it was elegant restraint. But Qanats also had weaknesses that helped them disappear or decline. They demanded skilled labor and constant upkeep. Sediment collected. Earthquakes, floods, construction, and neglect could damage tunnels. Expanding cities paved over routes or polluted recharge areas. Most importantly, powered wells changed the rules. A motorized pump can lift deep groundwater quickly, even when it lies far below an old Qanat tunnel. That can be useful in the short term, but if pumping exceeds recharge, the water table drops. When the water table falls beneath the Qanat intake, the ancient tunnel that once flowed by itself goes silent. In many regions, the new technology did not simply replace the old one. It undermined the conditions that made the old one work. This is the uncomfortable lesson. The Qanat was not a miracle machine that created water. It was a disciplined way of taking water slowly enough and moving it cleverly enough that settlements could survive in dry places for generations. Modern pumps can rescue farms from drought, support cities, and provide flexibility Qanats never could. But they can also hide depletion until the bill arrives underground. A Qanat makes scarcity visible. If the mountain recharge weakens, the flow weakens. If the community stops maintaining the tunnel, the water stops. Its limits are part of the design. The strongest payoff is that these desert tunnels were not just old plumbing. They were a complete survival strategy. Geology, gravity, labor, law, and patience turned into flowing water. Above ground, the desert looked empty. Below ground, people had built a quiet machine that let cities live where exposed water would vanish. If you want more stories about engineering that solved hard problems before modern machinery, follow Forgotten Engineering Files, because the next lost system may look simple until you see what problem it quietly defeated.